everyone. Welcome to our last Young Investigator Symposium. This is the 5th in our excellent series. If you've missed any of the symposia we've had so far, please look at our website and you can look at any of the symposium we've had along the way. So that's any of the 4 different ones. I'd like to first of all thank all the organisers we've had to help us put this entire thing together. That's Simon Krause, Sven Roger, Claire Hobday, and Renau Dong. So I'm happy to be sharing this session. Well, not sharing the session, but handing over the session to our chairperson today, which is indeed Claire Hobday. So Claire, please turn on your camera.
Hi, Jack.
Hi, Claire. So please take away some of these fantastic talks.
Thanks very much, Jack. Yeah, so it's a pleasure for me to be doing this final symposium here today. Something that's very close to my heart. So it's flexibility and stimuli responsiveness in framework materials. And we've got 2 great speakers here today. So first up, we'll have Stephen Dodsworth, who's from the University of Sheffield and also working at the Diamond Light Source. So he's going to tell us about some really cool in situ studies. And we also have Ben Wilson from the University of Windsor in Canada. And he's going to be talking to us about something else that's quite close to my heart, which is zirconium-based metal organic frameworks. So I think we've got a good session today. And I'd just like to get Stephen to turn on his camera and we can begin with the first presentation. Hi, Stephen.
Hello.
And I'll stop sharing my screen and I'll let you take your presentation.
Okay, good afternoon. Hopefully everyone can see my slides here. So thank you, Claire, for the introduction, and thank you to all the organisers involved in putting on this series of symposia and social sessions. I think it's been a really great event, and I'm delighted that you've invited me to be a part of that by giving a talk today. So as Claire mentioned, I've spent a lot of my time studying in the University of Sheffield. So for any non-UK viewers, Sheffield is located here in the north of England. And a quick Google search of the university shows you lots of nice images of our campus buildings. Unfortunately, being located in the north of England, it tends to look more often like this. And looking out of the windows today is no different, but there's not a lot else we can expect from that. So my project is also in collaboration with Diamond Light Source. So for those of you who aren't aware, that's the UK's national synchrotron facility. So it's located just outside of Oxford. And I've been lucky enough as part of my project to do a few experiments on a number of different beamlines, and I'm going to talk a little bit about some of those today. So I wanted to start my talk by giving a quick overview into some of the different types of dynamic behavior in MOF. So this isn't an exhaustive list, but I wanted to touch upon a couple here today. So to start with, we can talk about the ability to make and break bonds. So this can be in terms of coordination bonds. So we can have examples where frameworks are able to change dimensionality. So there's an example here in the schematic where you can go from a 2D to a 3D MOF through the installation of some pillar linkers. This also involves things like changes in the degree of interpenetration, and not limited to coordination bonds, but also things like post-synthetic modification. So I'm going to go into a little bit more detail about post-synthetic modification of framework materials later on in my talk. So the second example is dynamics of the organic linkers themselves. So we can construct dynamic frameworks through the pre-installation of linkers that are themselves flexible. So those which have the ability to rotate or more formally go through a cis-trans isomerism. So in the second example, we have a nasobenzene unit, which is able to reversibly isomerize, and that isomerism dictates the amount of CO2 that framework can absorb. And the final mode of dynamic behavior I wanted to talk about today is perhaps the most well-known or most talked about, and that's changes in the pore size or shape of the material. So this is when we talk about phenomena such as breathing and swelling, and in more rare cases, phenomena such as negative thermal expansion. So nearly everyone uses the example of MOF2020 as the sort of prototypical breathing MOF. So this is a framework which is able to reversibly switch between these two open and closed pore states, depending on whether the framework contains gas or it's been evacuated. So this type of breathing or flexible behavior is dependent on the ability of the coordination node to deform somewhat. And that's a feature of some of the frameworks that I'm going to talk about today. So we quite often attribute dynamic behavior in framework materials to host-gas interactions. So thinking about the absorption and desorption of small gas molecules. But we can also employ a whole host of different physical stimuli in order to prompt a dynamic response to framework materials. So things like pressure, temperature, light, if we're looking at photochemical changes, and perhaps there's even scope for electric fields and magnetic fields to be used, although there's perhaps not so many examples of those currently. But I think the key to really understanding these dynamic responses in these types of materials is the ability to perform in situ studies. So typically within our research group, we utilize in situ X-ray diffraction a lot, so the single crystal and powder diffraction. But there's a whole host of other techniques available, namely in situ NMR spectroscopy. We've looked a little bit at IR spectroscopy, but I'd highly recommend reading this paper from Stephen Dodsworth and colleagues, which gives a really nice insight into the different types of in situ studies that we can utilize to really understand the mechanisms behind these dynamic responses. So the material that I wanted to talk about today, this forms the background to my project, and also what I wanted to talk about today is a framework known as Shef61, so Shef being Sheffield framework. So this was work undertaken by Elliot Carrington and was published just before I started my PhD, and it involves this indium-based metal organic framework. So indium centers coordinate two amino terephthalate linkers to create this doubly interpenetrated diamondoid network. So you can see here the two different networks are shown in blue and red. And if you look along the A-axis, you can see these nicely defined lozenge-shaped channels which run throughout the structure. If you look along that channel length, you see this helical-like arrangement in which the two interpenetrated networks wrap around each other. So the framework's initially synthesized in DMF. So what's nice about this is we can grow single crystals of it relatively easily. And that means we can characterize it through single crystal diffraction. So crystallographically, we see residual DMF from the synthesis residing in the pores of the framework. But we're able to swap that out for a more volatile solvent such as chloroform. And we're able to do this while maintaining crystallinity. So again, we see this full conversion of the DMF to chloroform crystallographically. But we've also shown that this is the case in the bulk phase of material. So we use a number of different techniques, but I've shown here some solid state N15 NMR, which nicely shows that full conversion of the solvent. So if you're able to remove that residual solvent from the pores of the framework whilst maintaining the structure, or at least keeping some permanent porosity, then you can start to look at reintroducing gas in form of gas adsorption. So what's interesting about this material is that The framework has two very different adsorption isotherms, depending on whether you activate the material from DMF, so on the left here, or whether you activate the framework from chloroform on the right. So the reason for those different isotherms lies within the behavioral response of the framework to the removal of those guest species. So we can take single crystals of our initial framework containing DMF within the pores, and if we heat it up to a high enough temperature, what we see is that DMF can be driven out of the pores, and we're left with a transition to this, what we refer to as the closed pore form of the framework. So the pores narrow and reduce our accessible void volume. So rather than this being a defined transition between two discrete states like we saw for MOF53, what we actually see is a continuous breathing mechanism where we can access a whole continuum of structures from our most open to our most closed pore form. So starting off with here we see the framework is open, so this is in its solvated state, and we have this continuum of structures to the point where the framework is closed and that solvent's been removed. So we usually map these changes crystallographically by plotting the B and C axes. So those are the two dimensions associated with the pore width length. So this continuous breathing was shown to be fully reversible as well. So if you start with our desolvated closed pore form and just simply expose that framework to the atmosphere, the framework will absorb water and will undergo this gradual reopening of the framework. So when we start with chloroform in the pores of the framework and we do the same thing again, so we heat up our single crystals of these, what we see is that actually there's very little response or very little change in pore shape. And again, we can plot those unit cell parameters on overlaid with the graph we had previously, and we see that we only have this really small change in the B and C axis, so about an angstrom in both. So not only do we have this rather unusual continuous breathing mechanism, but we also have a framework which is displays different behavioral responses dependent on the gas present within that pore. So we have some sort of solvent dependency. So going back to our gas absorption and why we have two different shaped isotherms, we now know that we have our starting point is two very different pore forms of the pore. So the next thing we wanted to look at was how can we potentially modify the framework in some way that could alter these dynamic responses that we see. And one way of doing this in metal organic framework chemistry is through post-synthetic modification. So this is quite a common technique, and it allows you to change the chemical composition of the framework after you form that underlying coordination network. So it allows you to incorporate more complex or more sensitive functional groups that perhaps wouldn't survive the traditional harsh conditions of a solvent thermal synthesis, and ultimately allows you to tune the host gas chemistry of your framework. So for Shef61, we have a number of options in terms of modifying it. So we could exchange the indium, we could exchange the 2-amino terephthalate ligand, we could exchange the guest, so we've sort of already done this in terms of the solvent, but we could also swap out our cation. And we could also functionalize the 2-amino terephthalate ligand, making use of that 3-amino group. And that's what I want to talk about next, because that's something that I've been involved with. So the modification that we do is based around converting this 3-amino group into an amide group through reaction with acetic anhydride. So this is done in chloroform and under moderate heating. So we call this new framework Shef62. And what's really nice about this post-synthetic modification is due to the mild conditions required, you can do this in a single crystal to single crystal transformation, which means we can study the effects of this modification crystallographically. So when we do this, we see that we have a full conversion of this amino group to amide group. So this is modeled at full occupancy at a single site on our carbon ring. And again, we've done the characterization to show this is not only in individual crystals, but this transformation takes place within the bulk phase of the material. So again, we've gone to our solid state N15 NMR, which quite nicely shows the conversion from this amine to amide functional group. So if we look at the two frameworks side by side, again, looking down the A-axis, down that channel length, on the left we have Sheff61, and on the right we have Sheff62, our modified framework. So initially they look quite similar. We've maintained our overall interpenetrated diamondoid topology, but there are some subtle differences. So we have two different sites in the framework where adjacent linkers on the two different networks either point away from each other, in which case they're unable to form an interaction, or in the second case, they point towards each other. So for the Sheff61, they form this hydrogen bonding motif between the two amine groups. If we look at the same two positions on the modified framework, what we see is those positions have swapped. We now see those amine interactions replaced by carbonyl to carbonyl interactions of the modified amide groups. And the reason that those two positions switch is due to the fact that the post-synthetic modification drives this organic linker, the 2-amino terephthalic linker, to rotate 180 degrees. And it's this post-synthetic ligand flip that facilitates these new interactions between the two networks. And those interactions are optimized by a contraction of the A-axis. So the A-axis is shown along here. And you can essentially think of this as a spring which is compressing to optimize the geometry of those new interactions between the two networks. So the key question really for us was, what does this modification do to the overall flexibility of the framework? So we go back to our single crystal diffraction mapping study. So we start off looking at our Sheff61 framework in purple here. So we saw this really large change in B and C axis associated with the dimensions of the pore when we go from open to closed. If we plot the same single crystal diffraction data at various levels of desolvation for Sheff62, both from framework containing DMF in blue and chloroform in red, you quite quickly see that there's some key differences here. So the overall magnitude of this breathing behavior is significantly reduced. So it's about half when the framework contains chloroform, and about half again when the framework contains DMF. You also notice that the two starting points for the most fully solvated forms of the framework are quite different. So the framework containing chloroform is much more open starting point than when the framework contains DMF. And in another contrast to Sheff61, our original parent framework, we see that you can access the most closed pore form of the structure from either chloroform or DMF. So we no longer see that solvent dependency that we once had. And we can also map these changes in terms of looking at the A-axis against unit cell volume. So for Sheff61, we have this large change in unit cell volume, which is down to those changes in the B and C axis. But we see very little change in the A-axis, so that's the compression of this helical-like arrangement. However, when we look at the same data for Sheff62, the modified framework, what we see is a similar change in overall unit cell volume, but we now have a much more pronounced change in the A-axis. So essentially what we've done is modifying the framework. We've gone from a material that breathes in 2 dimensions, so just the B and C axis associated with the pore width and pore length, through to modification where we now have breathing in 3 dimensions. So we have a change in the B and C axis associated with the pore. Also, this helical-like arrangement undergoes a compression. And there's quite a neat little mechanism that allows this transition between the two-dimensional and three-dimensional breathing of the framework material. So if we look more closely at the crystal structure, we start in our solvated phase with chloroform. And we see these two methyl groups on adjacent networks, and they're pointing towards each other, but they're far enough apart that they can coexist quite happily. But as we gradually remove some of our chloroform, what happens is the A-axis contracts, we move along here, and that brings those two methyl groups closer together to a point where they're too close to coexist. And what happens is that contraction of their A-axis forces 50% of these ligands to rotate out of that plane to avoid this unfavorable steric clash. So once that ligand's flipped out of the way, we now have much more room available to further compress that A-axis, and that opens up a whole range of accessible A-axis lengths that we didn't previously see with our unmodified framework. So we're also able to demonstrate that this ligand flip is reversible. So this is from data from a powder diffraction study this time. So we start off with our open framework. We can remove the chloroform again by heating. And as before, if we just expose that closed framework to the atmosphere, you see that the framework will gradually reopen. So this last data point was taken after 26 days of exposure to the air. So we see that there's the potential that the framework cannot fully open, but it goes through that ligand flip. And the final thing that we wanted to look at was how does this post-synthetic modification affect the adsorption properties? So we can overlay the analogous gravimetric CO2 adsorption data. So these were all taken at 298 Kelvin. And we see we're somewhere in the middle of where we were in terms of Chef 61 chloroform and DMF. So it's not quite as high as this open pore framework, but it has a higher capacity than when we activate the original framework from DMF. So to understand the structural responses to these framework materials under positive pressure of gas, we take our samples to diamond light source, and we use a couple of the beamlines. So initially we used I11, which is the high resolution powder diffraction beamline. So the way this works is that we can pack our powdered sample in a quartz capillary and seal it inside this swage lock component, which we refer to as a gas cell. We can attach that gas cell onto a motorized stage, connect it up to a gas inlet, and although we're not able to continuously rotate our sample, we are able to rock this stage to ensure good averaging. So I11 is set up so that there's two different detectors, a PSD and a MAC detector, and we're also able to control the temperature through the use of a cryostream. So if we look at what happens to the framework when we increase pressure, so we started off looking at CO2 going from vacuum to 40 bar at 298 Kelvin. What we see is that even under relatively low pressures, you can force that framework to reopen. So you see a gradual expansion of the B-axis, concerted compression of the C-axis, and again that A-axis reopens. So you go through that ligand flip. And we've also looked at this using single crystal X-ray diffraction. So again, we put our sample on a mylar tip. So we start with the crystal glued to the mylar tip, packed inside one of these quartz capillaries, and that fits inside one of these gas cells, which again we can sit onto our diffractometer and collect diffraction data as under a positive pressure of gas. And so we did the same thing again, so CO2 at 298 Kelvin, and what we see is the framework is able to reopen as we gradually increase that CO2 pressure. So I'd just like to finish my talk by quickly summarizing. So we've shown that we can do a single crystal to single crystal post-synthetic modification of our quite unusual flexible material, Shef61. And the ability of this modification to go in a single crystal manner allows us to map the changes in flexibility due to that modification. So overall, we've gone from something that breathes in 2 dimensions to something that now breathes in 3 dimensions. So changes in the pore width and the pore length, but also a compression of this helical-like arrangement, which we didn't see before. And finally, we were able to show that this post-synthetic modification actually alters the CO2 absorption properties of the framework as well. And we've mapped these changes during gas absorption using some in situ studies. So I wanted to finish by acknowledging and thanking a few people. So firstly, my supervisor, Lee Brammer, Elliot Carrington, who's responsible for the initial work on the Shef61 framework and some of the post-synthetic modification of the framework, and the other members of the Brammer research group for all the help. Ashley Fletcher up in Strathclyde, who helped us out with the gravimetric absorption analysis. All the beamline scientists at Diamond Light Source who've either been involved directly with beamtime experiments or supervised my project in general. And finally, the University of Sheffield and Diamond Light Source for funding my project. And thank you for this, taking your time out of the day to watch my talk.
Well, that was really good talk, Stephen. I really enjoyed that. It always seems a bit weird clapping on the internet, but it definitely deserved a round of applause. That was a really interesting presentation. I'd just like to remind everyone that you can submit questions on the Google Forms. There's a link on the chat on the YouTube page, and there is a little time lag, so we'll let you submit your questions just now if you've thought of any. We do have a few at the moment. So I'll begin with the first question, if that's okay with you, Stephen. So we're starting with a big dog. It's Stephen Caskell has a question for you. And he'd like to know, and I think it's a really interesting question, what's the role of the particle size versus your post-synthetic modification? Do you see a role there?
So in some instances, we have seen that the post-synthetic modification can affect the particle size. It can cause the crystal particle size to become smaller. We've not really looked as such at the effects of particle size thoroughly. It's something that we've talked a lot about, but unfortunately we haven't had the opportunity to really look at that in detail. So there's lots of things in terms of looking at the difference. Some of the results from powder diffraction versus single crystal diffraction experiments, that we do see some differences there. So it's something that we're interested in, but unfortunately we don't really have any sort of clear evidences yet.
Okay, yep, I think that's cool. So I've got another question here from Jack. It's kind of more related to the gas absorption part. So do you observe hysteresis during your breathing process?
There is a slight hysteresis, yes, not very much. So these are all typically type 1 adsorption isotherms. When we do the offline data and when we do the in situ studies, again, we see there's a slight hysteresis, but nothing noticeable. So the interesting thing about the original framework is that if you partially desolvate it, you get a gated adsorption, which I didn't talk about today. But you can read all about that in the initial publication.
So I've got a final question, if that's okay. I'm the chair, so I assume it is. I was wondering if you've had a look, I know it's not your group speciality, but if you're collaborating with anyone to do any computational studies to do with the ligand flip, it seems really a really exciting and cool transition.
Yeah, it's definitely something that we're hoping to do very soon. It's something we've talked a lot about, and it'd be really nice to have the computational side of things to back up what we've seen experimentally. I mean, there's a few other sort of intricacies which I didn't really talk about today, but yeah, it'd definitely be nice to have the computational side of things to go alongside what we've been able to do experimentally.
Okay, that's great. Well, thanks very much, Stephen. We've got a couple of questions in the chat, so if you could reply to them on the Google Sheet, that would be great, because we don't have any more time just now. But you've got the link there as well, and Stephen will reply to your questions. If you've got any more, just stick them in the Google Doc. That would be great. Thanks, Stephen.
Thank you very much, Claire.
So now it's time for our second presenter. So I just ask Ben to turn on his camera and his microphone. Hi, Ben.
Hey.
How's it in Canada this morning?
Starting to get cold.
Starting to get cold. What's cold like?
Maybe if we get a lot of snow and wind, you get a 14 in the middle of winter, but it's not that bad most of the time.
Yeah. Okay. Cool. Nice. So do you have your presentation ready to begin? Okay, that's great. So I'll make myself disappear and I'll let you continue with your presentation. Thanks very much, Ben.
Thanks. So in this presentation today, I'm going to be going over some of the recent work that we've been doing in the LOBE group, which is based at the University of Windsor in Canada. And I'm going to be talking about how we have been working with some zirconium type MOFs and using them to embed various types of rotaxanes, both degenerate and non-degenerate type molecular shuttles. So just a bit more about where I'm from. So I'm from Christchurch in New Zealand, and I did my PhD and as well as undergrad at the University of Canterbury. And I was actually lucky right at the end of my PhD to get to use the labs in this brand new building here. And you can kind of see the old, slightly not as nice building in the corner here. And I was quite lucky that during my PhD, I got to spend quite a bit of time working in labs in Bordeaux and France, obviously, of course, famous for its wine. And right now I'm based in Windsor, which is, I think, about the furthest south you can go in Canada. So this is actually the waterfront of Windsor here, and this is Detroit. That's the GM building. And so I can literally see Detroit from the end of my street. So just to start off, as this is a talk for MOF chemists, I'm going to give a sort of a brief overview of mechanically interlocked systems, as some of you may not be too familiar with them. So I'm going to be discussing rotaxanes, which are made up of a ring threaded on an axle. And while the ring and the axle aren't actually covalently bonded, they can't be separated without breaking covalent bonds due to these bulky stopper groups at either end. So typically these rings are bound by a recognition site on the axle. And if there's multiple recognition sites along the axle and the ring can move between them, the rotaxane behaves as what's known as a molecular shuttle. So one of the earliest examples of this is this quite cool system here by Stoddard, where we have this pyridinium ring and this long polyether axle. If we're thinking about using these as ligands and MOFs, the system here is very large and very flexible, so it isn't really an ideal starting point. So what we work with in the LOBE group is these slightly more rigid and compact systems, typically on these 8-shaped type axles with these benzimidazole recognition sites and these crown ether macrocycles. And this gives us a nice starting point for designing ligands and MOFs. So as I mentioned on my title slide, I use the phrases degenerate and non-degenerate molecular shuttles. So a degenerate molecular shuttle is when the ring moves between two recognition sites which are chemically the same. And so there's been a couple of examples reported of these degenerate type molecular shuttles in MOFs. The first one by the Loeb group was UWDM4, or University of Windsor Dynamic Material 4. As all good MOFs have an overly long acronym. And we can see that in this case here, with this H-shaped axle, we have these two recognition sites in green, and the rate at which the ring will move from left to right is exactly the same as it moving from right to left. And more recently, we reported these two compounds, UWDM8 and UWDM9, when we put this molecular shuttle into a MOF, and I'll be talking a little bit about these in my presentation. Once again, we have two chemically identical recognition sites. If instead the two ends of the rotaxane are different, for example, here we have this one in green with these phenyl stopper groups, but at this end we have this one in orange with these bromo stopper groups. This makes things a little bit more complicated, as the rate at which the ring moves from green to orange is different from the rate at which it moves from orange to green, as the ring has different affinities for each of these recognition sites. And so this is what I'll be finishing off my talk with, the MOF containing this non-degenerate molecular shuttle, which is UWDM11. So in terms of how we can actually go about building MOFs with these types of rotaxane linkers, one strategy is known as the cross-linking approach. And so this is what was used in UWDM4. We took this H-shape type axle here, and each of these sides we refer to as struts. And they each formed with these zinc nodes a PCU lattice. And these PCU lattices were joined by this crossbar here. So overall, this gives an HEA net. And along this crossbar, we have these two recognition sites. And this is where we see the shuttling of this macrocyclic ring. So more recently, we've been focusing on zirconium type systems due to their higher chemical and thermal stabilities. In particular, derivatives of UiO68. So those of you familiar with these family of MOFs know that the FCU topology has these octahedral and tetrahedral cavities and these zirconia nodes. So our approach was quite similar to UWDM4, where we use this slightly longer crossbar here. Now it's a biphenyl, and we cross-link the tetrahedral cavity of UiO68 derivatives. So this cross-linking rotaxane occupies two edges of the tetrahedron. So there are remaining four, which are made up by either this coligand here, where we have this tetramethyl phenyl spacer, or this coligand here, where we have this deuterated phenyl spacer. This is, of course, the parent ligand of UiO68, and this one here is a derivative of UiO68 PCN57. And the reason why we have these deuteriums here becomes important when we look at using solid-state NMR to study the dynamics in these systems. So I'm not going to spend too much time with this organic synthesis, being this is the MOF conference. The main reason I have this here is to point out the fact that in these ligands, what we do is we enrich one position of the benzimidazole recognition site with carbon-13. And we can do this reasonably easily, starting with carbon-13 enriched dimethylformamide. The reason why we need to be able to carbon-13 enrich this position is so we can get sufficient signal in the carbon-13 solid-state NMR that we can work out basically what the ring is doing, as the chemical shift of this carbon here is very sensitive to whether here it's free, or in this case here it's binding the crown ether macrocycle. So in terms of what these cross-linked tetrahedral cavities actually look like, so when we take this ligand and either the tetramethyl coligand to give UWDM8, or this deuterated phenyl coligand to give UWDM9, D4, because of these deuteriums. And we built these models in Material Studio just to get an idea of what these tetrahedral cavities will actually look like. So in the case of UWDM8, we can see these tetramethyl coligands, these central spaces are perpendicular to the linker plane with these methyl groups orientated directly in to the tetrahedral cavity. And they're locked in that position due to the steric bulk of the methyl groups, and they're potentially going to impede any translational motion of this macrocycle from this recognition site that is currently at in orange to the other one. Things are a little bit different when we look at UWDM9, as we have this less sterically congested ligand. So not only do we have more vacant space, we're potentially allowing this macrocycle to move from one recognition site to the other, but we also have a second dynamic group in here, this phenyl ring, which can act as a molecular rotor, hence the deuteriums that we can use to study that using deuterium solid state NMR. So if we just first start off with the carbon-13 solid state NMR, which we use to look at understanding the position of this crown ether macrocycle. For UWDM8, when we have this tetramethyl spacer, which is perpendicular to the linker plane, when we conducted the VT variable temperature solid state NMR measurements, we saw across all temperatures, this is just a room temperature spectra here, 2 peaks corresponding to this carbon-13 enriched position. So the upfield peak corresponds to the unbound recognition site, and this one here in red corresponds to the downfield. The downfield peak corresponds to this recognition site binding the crown ether macrocycle. And as we see simply 2 peaks across all temperatures, that indicates that any motion is slower than the NMR timescale, and this effectively means that we have shut off any translational motion and we have the ring locked at one end or the other. And this makes sense when we consider the steric bulk imposed by this tetramethyl phenyl spacer. Things, of course, are different when we have UWDM9, as we have this less bulky ligand, which is also able to rotate in and out of the linker plane. So we see a single peak at all temperatures corresponding to the unbound recognition site. And so this means that the ring isn't actually binding at either recognition site, and we believe it simply sits about the middle of the axle here. And this is the sterically least congested position, as it's away from these tight corners of the tetrahedral cavity, which are quite sterically demanding when it's binding at this recognition site. As it occupies this position here, it's potentially going to be coming into contact or interacting with this phenyl rotor of the coligand, and we can probe that further with deuterium solid state NMR, as this technique is very sensitive to the rotation of deuterium nuclei. So it's really useful for characterizing these types of molecular rotors and MOFs. So what we did is we conducted VT measurements on both UAO68 with this deuterated coligand and UWDM9 with this deuterated coligand and this cross-linking rotaxane linker. And so when we carried out these deuterium NMR experiments, we could see significant changes in the NMR spectra upon going from UAO68 to UWDM9 D4. And the Sherco research group down at Florida State University did an amazing job of going through and simulating all these different types of rotational motions and the deuterium NMR spectra. And what they were able to show is that I think the key difference upon adding this cross-linking rotaxane linker is that we add a third energy barrier for rotation that impedes the movement of this molecular rotor here. So what's nice in this system is while we get these sort of 2 dynamic components interacting, we don't see the translational motion, which is what we initially set out to have occurring inside these zirconium-based MOFs. So we had to rethink our strategy a little bit. So obviously, if the tetrahedral cavities are too sterically confined, the obvious solution is to simply put the rotaxane in the octahedral cavity, which is larger. So this, in terms of the cross-linking approach, is quite challenging because it's quite a long distance across this octahedral cavity of about 23 angstroms. And this means that simply designing one of these H-shape type linkers that can cross-link this is not that straightforward, as there's not a nice even number of phenyl rings that we can simply make into the axle that will stretch across this cavity here. Instead, we decided to make things a little bit easier for ourselves, and we simply appended this 2-rotaxane molecular shuttle onto this linear dicarboxylate here. And the reason why we chose this approach is this rotaxane protrudes about 13 angstroms, so will fit in the octahedral cavity, but it's too big to fit in the tetrahedral cavity, so we can still control the position of the rotaxane in the MOF. As a consequence of appending the rotaxane in this way, as I've highlighted here, we have now two different kinds of recognition sites, and we have a non-degenerate molecular shuttle. And this is going to have some quite major implications in terms of the dynamics that we observe, both in solution and the solid state. So I promise this is the last slide of organic chemistry. Just wanting to point out once again that simply starting from this carbon-13 enriched dimethylformamide, we can selectively enrich one of these recognition sites with carbon-13, and selectively enriching one side and not the other, as we have this non-degenerate system, is quite important, as that makes characterizing it via the carbon-13 solid state NMR much simpler. So whenever we synthesize a new rotaxane, the first thing we do is we take the ester form before we hydrolyze it for making this carboxylate linker, and we characterize the dynamics in solution via variable temperature solution NMR, in this case carbon-13, as we have this carbon-13 enriched position here. So when we do these dynamic type NMR experiments, what we're looking to see is at high temperature, we have a single peak corresponding to the chemically averaged environment as the ring moves very rapidly between these two different positions. As we cool it down, this peak, in theory, will broaden out, and then the motion will slow sufficiently that we see both of these forms on the NMR time scale as the motion is slower than the speed at which the NMR operates. And when we see both the single peak at a high temperature and the two peaks at low temperature, we can then start to simulate the NMR spectra and extract things such as the energy barrier for translation, and we can work out the rate at which it moves at each of these temperatures. Unfortunately, with this system here, we have very rapid translation. So while we know that we have translation occurring as we see a single peak corresponding to this fast motion, even at low temperature, so this is the lowest I could get the spectrometer down to, 210 Kelvin, we're still not seeing this peak broadening and separating out into two distinct peaks. So we at least have a handle on how fast this is operating, but we can't exactly quantify it. One of the nice things that we're able to show in solution for these types of molecules is that they are very sensitive to pH. So this is a crystal structure of the neutral rotaxane, and in solution, this chromium macrocycle moves very rapidly between these two neutral benzimidazole recognition sites. If, on the other hand, we add one equivalent of an acid, we typically use HBF4, we'll protonate this benzimidazole ring, and we selectively protonate at this phenyl stop at end of the rotaxane, and this also locks any translational motion. So the ring is locked at this recognition site. So this means that at least in solution, we've been able to switch off the translational motion by adding acid. And this is something that we like to translate across into the MOFs. And this is one of the key reasons why we're working with zirconium systems, which is stable enough that we can add acid and they're not going to decompose. So we took this, we hydrolyzed the esters to make the diacid, and we made them off, much like the previous examples. And this is now UWDM11. So just one of the nice things about this material, as we can see from PXRD, that we can activate it, we can add acid to it, we can then add new guest molecules to it, and we don't see any structural changes or loss of crystallinity. So this is a very nice, robust system that we can do a lot of things with that are going to affect the dynamics in the solid state. And once again, this is why we're working with these nice, robust zirconium type MOFs. So in terms of what this octahedral cavity actually looks like, we have this on one edge of the octahedron, we have this appended rotaxane, and we can see there's plenty of vacant space in terms of when we have the activated MOF for this ring to move from this recognition site to this one. Of course, as we're in the octahedral cavity, these methyl groups are pointing into the tetrahedral cavity, so they're not going to have any steric blocking effects that we saw in UWDM8. So we started off by activating the MOF and measuring the carbon-13 solid state NMR. So as we can see, this is this peak here, which is nice and strong as our carbon-13 enriched environment. And as we cool down, We start at room temperature with one peak corresponding to fast translational motion. And even at 173 Kelvin, which is the limit of our solid state NMR, we still simply see one peak. So while it's nice to know that when we put the when we put the Rotexane in the octahedral cavity, we get fast translational motion. We're not able to quantify it in terms of a rate or an energy barrier, as we're not seeing this peak separate out into two distinct peaks at low temperature. So what we have is an issue of scale. So when we do these dynamic type NMR experiments, what we need is the fast translational motion at the high temperature to be faster than the NMR timescale, and then the slow translational motion at the lowest temperature to be slower than the NMR timescale, which is not what we have occurring. We have both of these faster than the NMR timescale for activated UWDM11. So what we need to do is find a way in which we can sort of slow down the motion. So the fast translational motion at high temperature is still faster than the NMR timescale, while the slow translational motion is now slower than the NMR timescale. So there's a number of ways that you can change the rate of translational motion in these Rotexane type systems, most of which involve going away and doing some more organic chemistry and modifying either the ring or the axle. However, we decided, since we're working with MOFs, we were going to use a different approach. And we instead decided to introduce guest molecules into the cavity of the MOF to see if we could increase the sort of effective viscosity of the system or the microenvironment that this Rotexane is experiencing, and see if that would slow down the translational motion. So what we did is we took our solvent molecule, which is mesitylene, and when we load that into a MOF, people have shown that by adding solvent molecules into the pores of the MOF, and as they're confined in there, that can result in an increased effective viscosity. And people have demonstrated this with systems where they're looking at molecular rotors in MOFs. So we chose mesitylene as it's retained quite nicely by the MOF. So this is just a TGA, which shows we don't really lose too much if we leave the MOF sitting out of the solvent, which means it's nice in terms of preparing a sample. We know we're not going to be losing all the guest molecules as we make up the sample for the solid state NMR. The other reason why we chose mesitylene is it's very non-polar, and it doesn't have anything which is going to interact via a hydrogen bonding type interaction, for example, with the benzimidazole moiety on the Rotexane. And this is important as we don't want to introduce competitive binding, which is going to have a significant effect on what the crown ether is doing about those benzimidazole recognition sites. So we went back and for now UWDM11 with mesitylene in the pores, we remeasured the carbon-13 solid state NMR. And we can see when we go down to 173 Kelvin now, we now get two sets of smaller peaks. Sorry, a smaller peak sort of upfield and a larger peak downfield, corresponding to this carbon-13 enriched position. So the downfield peak, as we know from solution, corresponds to the bound recognition site, while the upfield peak corresponds to the unbound recognition site. So as we've got these uneven peak sizes, this is as a result of this being a non-degenerate molecular shuttle, and the ring having a high preference for this terphenyl stoppered carbon-13 enriched end. And this is in line with what we're seeing in solution for these systems, where these phenyl rings actually stabilize the binding of the crown ether here, as opposed to these bromos at the other end. We can see as we start to warm the sample up, we get coalescence of approximately 273 Kelvin. And that allows us to start to estimate some approximate energy barriers for this translational motion. So at 173 Kelvin, you can see that it's approximately 78% at site A, which is this end here, and 22% at site B, which is this end here. And with coalescence occurring at about 273 Kelvin, we can approximate an energy barrier for translation from going from site A to site B is 13.2 kilocalories per mole, and from site B to site A is about 12.5 kilocalories per mole. So this makes sense that the site that the end of the ring has a stronger affinity to, has a larger energy barrier to break for it to move to the other recognition site. So in terms of evaluating the exact effect of solvent on dynamics, if we first start with UWDM4, which was, I mentioned right at the start of this presentation, was the first example of one of these molecular shuttle type systems. We're able to measure the energy barrier in solution for this translational motion was 7.7, and then when we measured the solvated MOF, it was almost double at 14.1. However, unfortunately, we weren't able to measure the activated form as the framework collapsed. However, with the zirconium system, while in solution, we weren't able to extract a rate. We simply know it's translating faster than the NMR timescale, even at the lowest temperatures. We were able to measure both the activated form, where once again, we knew the translational motion was fast, but we can't exactly quantify it. And then we could slow it down when we added the solvent and approximate these these energy barriers here. So this is what makes this UWDM11 material quite nice in terms of evaluating dynamics. Is because it's very robust. We can measure both the activated and the solvated form without any significant structural changes occurring upon removing solvent or adding solvent. And we can move towards evaluating the effect of solvent in the pores and the MOF on the dynamics of these types of systems. So this brings us to this question here, which I started looking into more closely in the group, which is, do some types of the dynamic motions of these rotaxane type systems, when they're in the MOF, have more of a solvent effect of having solvent than others? For example, if we think about this translational motion, which I covered in this presentation, the volume occupied by the ring changes as it moves from one recognition site to the other, which when we have a solvent-loaded pore is going to result in reordering of the solvent. However, if we think about rotation, where the volume occupied by the ring doesn't change significantly during its rotational motion, this is going to result in effectively negligible reordering of the solvent. So potentially the nature of the solvent or the presence of it is going to have a much smaller effect than in systems where we're looking at translation. So just to summarize what I've covered in this presentation, with these UAO68 derivatives, we can cross-link the tetrahedral cavity with degenerate molecular shuttle-based ligands. However, while we can control the position of the macrocycle based on the nature of the co-ligand, we don't get any motion between the two recognition sites. However, if we instead append a non-degenerate molecular shuttle into the octahedral cavity, we can get translational motion, which is dependent whether on the MOF is activated or solvated. And so in terms of where we're looking at moving this work in the future, as I alluded to a couple of times in the talk, one of the nice things about these benzimidazole-based recognition sites is their sensitivity to pH. And I mentioned that when we monoprotonate the linker, we can switch off the translational motion. We can also diprotonate the linker, and that switches back on the translational motion. It's just slower. And as we're now working with these nice and stable zirconium systems, we should be able to synthesize the MOF and then protonate it and be able to change up the dynamics with this external stimuli. So I'd just like to finish off by acknowledging all the people who have helped me with this research. My boss, Professor Steve Loeb at the University of Windsor, Dr. Hazla Golomi, who was a previous PhD student in the group who started off this degenerate molecular shuttle work. And then also Rob Shurko and his group, both at the University of Windsor and down at Florida State University, for all the expertise with these solid state NMR measurements that I've shown you today. And thanks to the organisers for giving me this opportunity to present.
Thanks very much, Ben. That was a great presentation. I love seeing all these presentations about molecular machines. You always have very good graphics and it's very easy to follow. Really enjoyed it. So I'd like to remind everyone who's watching on YouTube that you can either put questions into our chat or also into the Google form. We do have a couple of questions on the Google form at the moment, and we'll start with a question that I also had, and it's at the bottom, I think. It's from Jack, and it says, can you quantify how many non-degenerate shuttles containing ligands are located in each octahedral pore? That was something I was thinking about as well.
Yes, so if we decompose them off and run the NMR, we can work out the ratio of the rotaxane linker to the co-ligand in there. And so it works out to be about just under 1 rotaxane per octahedral cavity.
Okay, cool. So it would always be pointing into the octahedral pore because they don't have any space to point out to the tetrahedral pores. Yeah, cool. We have a question again from Stephen Caskell. He's an avid watcher of us young MOF researchers. And he said a nice talk. And I suppose you touched on it a little bit, but not about loading, but just with solvent in general. But is it possible to measure dynamic NMR in situ with gas loading?
So this is something that we have thought about that will be really cool to see, obviously measuring different pressures to see the effect. It's not something that I think we've done in the past with our solid state NMR setup. I'm sure it's possible. I'm sure people do it. But it would be really interesting to see different gas pressures and different vapors in there.
Yeah. And then I had another one where I was wondering if you thought it was at all possible to make a sort of rotor out of the tetrahedral system. So you said the reason that you couldn't was because that sort of middle benzene ring was interacting with your shuttle. Could there be like another group that you could put in the middle of those two benzene rings that would facilitate that, or do you think that tetrahedral pore is just too small to begin with?
So I think the issue with the tetrahedral cavity is obviously with the phenyl, we have tried some other things in the middle, which are not that bulky, but we see the same behavior if it just sits in the middle of the axle. And I think the issue is even if there's enough room for it to sit in the middle of the axle, that then becomes more favorable than sitting at the corners where there's those quite tight angles based on the tetrahedron. So potentially one of the things we have considered is if we make the middle point of the axle less favorable for the ring to occupy, such that it then would sit at one recognition site but still be able to move to the other one.
Yeah, okay. Yeah, that's great. So if anyone has any more questions for Ben or for Stephen, you can put them into our Google Doc and they'll try their best to answer your questions. I'd just like to thank Ben and Stephen again for presenting today, and tell all your friends and all your colleagues that this is live on YouTube for the foreseeable future to watch at your own time. If there was a bit that you missed or something that you'd like to catch up on, it's at the link that you have just at the moment. And I'd just like to share one final screen with you today, and that's a reminder of our final Young Investigator Symposium social. So I've made a little image out of our social that we had last Friday, where we were simulating with our hands, making models of all of the vibrations in, I think it was a water molecule. So you can see we've all opted for different vibrational modes. And it's our final one. So if you want to come and join in, you can get the link on this QR code, or you can also sign up to our emails on the website and you will get a link to the Zoom call. And this one is for the Europeans, and for those more east, it is an evening call. Sorry, Ben. But if you want to join us for a beer and this pub quiz, that would be really enjoyable. So yeah, so I'd just like to say thank you for attending our Young MOF Symposium, and we hope to see you at the MOF2020 conference, which begins next week. So yeah, I'll just see you all there, and bye-bye for now.